So this is PHY 205, thermal physics. PHY 205, thermal physics. And it's 2 units. That means 2 hours every week or 1 hour other day. My name is Dr. Ogungbemi K.I. I will not be the only teacher taking this. My colleague that will be taking this will be Dr. Adedokun, MB. Dr. Adedokun, MB, will be the second teacher taking this. My office number is given to you there, 307, room 307, Physics Department, Faculty of Physical Sciences and Physical Sciences and Earth Physical Sciences. Then my telephone number is as shown, and this telephone number is WhatsApp compliance. It is, can you see my screen?
Yes, sir.
Okay, good. So, what am I talking about now? The telephone number is WhatsApp compliance. My email is also given to you there. So that means I'm accessible to you physically if you come to my office. If you don't want, you want to communicate through WhatsApp, yes. You want to communicate through the email, maybe. And that's why I've given you my full information. The second teacher, when she comes, she will introduce herself, okay? She will introduce herself when she comes. All right? Okay. So here we are. The course. The attendance, students enrolled in this course are expected to make 65% attendance at lectures to be eligible for the exam. Before you can sit for the exam, your attendance must be at least 65%, including today own. We are going to take attendance. Is the class rep there? Hello? We are going to take attendance. So evaluation. The course will be evaluated in 2 parts. 1, continuous assessment. 2nd, an examination. In the continuous assessment, the maximum obtainable score there will be 30% or 40%, depending on how we consider that. That will be your continuous assessment. And the continuous assessment is made up of your class test. That means you'll be given a class test. You'll be given homework. Homework is not an individualistic stuff. It is a kind of a collaborative study. Then class participant. As we are going, I'm going to ask questions, I'm going to talk. I expect you to talk back to me because I'm not a pastor or imam that is preaching. Class should be two-way communication, okay? So when I ask question, you answer me, I get your matric number, I record, you score a mark. Yes, you score a mark. So that is what I call class participation. So make sure you're active in this class. Don't be a dormant student in this class. And another aspect is that we also take you in attendance. Attendance, we carry mark. Attendance, we carry mark. So the continuous assessment, which may be 30% or 40% of the total mark, will be based on class tests, homework, class participation, and class attendance. So at the end of that, examination. So if we decide that the continuous assessment is going to be 30%, you should know that your examination should be 70%. And the final marks based on that will be 100%. So continuous assessment, 30%, examination 70%. And if you take the second route, whereby the continual assessment is 40%, your examination will be 60%. You add the two together, you're going to get 100% in total mark. That is the way out. So with this, you must be able to map out how you can pass this course. How you can pass this course. We already laid it down. And that is the easiest way to pass the course. Any question about these slides? Any question? I already told you somebody should talk back to me at any time when I ask questions. So if you want to talk back to me, just mention your name or matric number, I'll put it down. I say I don't like a dull person on my class. There must be mark for participation, and it starts right now. So course content. Yeah, is the course content? Yeah, is the course content? Yeah, some people have started putting their name down and their matric number. Yes, do that. That is what I'm going to save as my class attendance. Thank you. Yes, that is what I'm going to save as my class attendance. Everybody should go to chat arm of the discussion, put your name down, matric number, your department. Like I have Odulaja Daniel, Adekunle Physics Education, Oyebanji, Pastor Covenant. Is that your name? Put your real name down, because I will not be looking for lost name. Put your name down, the name you registered.
Yes, sir, that's my name, sir.
Huh?
That's my name, sir.
Okay. Shogbamu Ademola Emmanuel, apply physics. So just go ahead as they are entering, tell them they should populate the attendance. Thank you. So as I was saying, the course content, excuse me, the course content or the course outline is as given. We're going to talk about the foundation of classical thermodynamics. We're also going to define some terminologies that are relevant to the course itself. Yes, definitions of temperature and other terms. We're going to define the first law of thermodynamics. We're going to define what work, energy, and internal energy is. The second law of thermodynamics, Carnot cycles and Carnot engines. The zeroth law, entropy, irreversibility, thermodynamic potentials, and the Maxwell relationship. Ideal gas equation, internal energy, and internal molecular modes. Qualitative discussion on phase transition, Gibbs free energy, Clausius and Clapeyron's equation, example of phase transitions, van der Waals, kinetic theory, main free part, equal partition of energy, heat transfer, and heat itself. All these, we are going to be discussing on this as we go. So this course content has been subdivided into two. The first aspect, I will be taking it, and the second aspect, the next lecturer will come on board and take that. So I believe you will do this. I will give you the slides at the end of the class. But as we go, I will also give you notes along the line. So the first question is, what is thermodynamics? What is thermodynamics? The simple definition of thermodynamics is that the study of thermodynamics is concerned with ways energy is stored within a body and how energy transformations, which involve heat, work, may take place. The study of thermodynamics is concerned with the ways energy is stored within a body and how energy transformation, which involves heat and work, may take place. And we can approach this in two forms. We either go through the macroscopic way, which will be the classical thermodynamics, of which we are starting with. We study large numbers of particles or molecules that make up a substance in question. And we do not require the knowledge of behavior of an individual molecule. Or we can go through the microscopic statistical thermodynamics. It's concerned within the behavior of an individual particle of a molecule. And we'll talk about the average behavior of a large group. So in other words, our thermodynamics can be approached either from the macroscopic or microscopic aspect as defined. Excuse me, let me permit these people to come in now. Let's look at them. Where are those people waiting now? Are they really waiting, or they are everybody's on, I believe? Yes. I think everybody's on. I don't have to keep waiting. So we roll ahead. Okay. So we roll ahead now. Understanding thermodynamics. Why do we have to study thermodynamics? What are the necessary things? Since it is a subject that has to do with energy flow and how energy is stored, prediction of spontaneity of processes, molecular basis of thermodynamic quantities. All these, we are going to talk about it as we go. As we go. I don't know how these people are entering. Maybe it's my fault. I was saying I will admit them. Next time, I will not put admit there. I just leave the class open. So based on postulates, not based on microscopic or molecular description, the word equilibrium state can be described as where we have a physical observable that goes through a classical thermodynamic process to produce an abstract quantities. And when you talk about physical observable, what do we mean? We are talking about the volume of a system, the pressure of a system, the temperature, number of molecules, or the chemical identity of the system that we undergo classical thermodynamic process to give us more information about the internal energy of the system or the entropy of the system. So the observable come out after your thermodynamics process to give you an abstract quantities. And this abstract quantities we are talking about is the internal energy and entropy of the system. Internal energy and entropy predict heat, work, and spontaneity of a system. So we are going to talk about the conversion of energy, that is to say, heat or thermal equilibrium. Then we talk about the work, which can come in form of mechanical equilibrium or otherwise. And we also talk about the chemical reaction or the physical reaction in the transitional going from one stage to the other, one phase to the other. Let's define some terminologies here. When we talk of a system, if you see yourself as a system, then you are in an environment. Your surrounding becomes your environment. There's a boundary between you and the environment. So in this case, we have three terminologies now: a system, that has boundary with its environment. System within the environment, and there's a boundary there. So thermodynamic systems are quantities of matter or a region of space chosen for study. That is to say, the portion that is of our interest is what we call the thermodynamic system. And this system has what we call real or imaginary boundary or layer that separates it from its surrounding. So boundary is real or imaginary layer that separates the system from its environment or surrounding. When we talk about surrounding, we're talking about the physical space, outside the system boundary. So we have three things. You must be able to define them: surrounding, system, and boundary. So when we talk about system can be two. We have what we call a closed system and open system. System is divided into two: closed and open system. A closed system is a system that allows energy to flow into it, but the mass cannot flow in or out of it. A closed system is a system of fixed masses. Within the boundary, masses are not allowed to flow through. It is a closed system, but energy, yes, can flow through the boundary to the surrounding. That is a closed system. A closed system permits the flow of energy between the system and the surrounding through the boundary, but the mass will not be allowed to move. We have a movable closed system whereby you compress a gas, release a gas, and you expand a gas. In as much as it is a closed system, it is only mass that remains constant, but the energy can be exchanged between the system and the surrounding. The other one is what we call the open system. A system is termed open system when both energy and mass is allowed to cross through the boundary to the surrounding. In other words, there is an exchange of mass and energy between the system and the surrounding through the boundary. So it is only the volume that controls this. So take note of that, and you must be able to define that. It's a terminology you need to remember if you are taking this course. A system can also be termed as isolated system. A system can be termed as isolated system. And what is an isolated system? An isolated system is a closed system where no heat or energy may cross the system boundary. There is no heat or energy crossing within the system boundary. And typically, a connection of the main system, several systems, and the surrounding is considered as isolated system. So a system in which work is done into the system, mass is moving, but energy can be released from it, as you see it in the diagram below. So let's look at it in a broad perspective. From the first postulate, energy is conserved. That is what the first law of thermodynamics is talking about. In summary, we are still coming to deal with that. The summary of that is talking about the conserved energy. So for an isolated system, the internal energy of the system now is also equal to the internal energy of the system later because it's isolated. So the change in internal energy of an isolated system is zero because the internal energy before is also internal energy after. So the difference between the two will give you zero for an isolated system. A closed system where no mass is allowing or out, in other words, heat energy is supplied into the system, work is done into the system, the change in internal energy will be the sum of the heat supply and the work done into the system. The sum of heat supply and work done into this system. In other words, delta U equals to Q plus W. Q is the heat supplied to the system. W is work done to the system. For the adiabatic system, when you talk about adiabatic system, that is a system that occur, a process that occur at a constant temperature. The temperature does not change. In other words, there is no heat flow in or out of, there is no heat flow into the system, no exchange of heat in the system. Such a system is termed adiabatic system. Only work is done into that system. That guy should mute himself. Oh, just mute yourself. Don't disrupt us because you are just coming now. Tell him to mute himself or herself. I'm looking for him now. I will call his name out now because he's just coming and he's trying to disrupt my class. You are not going to find it easy. And who is that guy now? Mute yourself. If not, I will send you out of the class. Mute yourself. If not, I will send you out of the class. You see how you are disturbing my class now? Okay, let me just get you. Where is it, participant? Okay, go ahead. Show me the people that are here now. Yeah, it's Joy. It's Joy that is disturbing us. It's Joy that is disturbing us. And I will remove you from the class. He has already run out. So, Joy disturbing my class. I will note it down. That's my pen. So that I will be after you, either you like it or not. Joy. Another one is disturbing again. You see how you are disturbing my class? Using my personal money for data, and you decide to waste my time. Michael, you are the one disturbing the class. Michael.
Sir, I'm unmuted. I'm not.
Yeah, you are, because I can see a dot moving up and down. Ikudeibo. What is that dot all about? Remove it.
I don't
okay,
know.
Let me remove you. Don't worry. When I remove you from the class, you are wasting my data, wasting my money, personal money, because I want to teach you, and you are still making the class unbearable for us. Any change. All the properties of the system are known and are not changing. They remain constant. Thermodynamic equilibrium. That is a state of balance. A system is in thermodynamic equilibrium if it maintains thermal equilibrium. And instead of thermal equilibrium, we are talking about constant temperature, uniform temperature, mechanical energy, and so on and so forth. Everything remains in equilibrium. There is no change of any thermodynamic property. That is, the state is said to be in equilibrium. Other terminologies that we needed to know is process. Process. What is a process? That is when a system changes from one equilibrium state to another, it undergoes a process. When a system changes from one equilibrium state to another, that is what we refer to as a process. And there are many types of processes. The first one is isobaric process. Isobaric process is a process whereby the pressure of the system remains constant. All other observables can change. But in as much as the pressure remains constant, we refer to it as isobaric process. Other processes are isothermal process, isochloric process, and isotropic process. All these are uh, very useful, and we are still going to talk about that maybe in the other phase of the system. So when they say define process, you should know what a process is. But when you're talking of a system can also go through different paths to get to its end point. So we have what we call path. Path is series of states which a system passes through during a process. Series of states which a process passes through during a change. So that is it. Look at the compression now. When you want to compress a gas, you move from the first volume, which is higher volume, to a lower volume. The path takes is a process. The part of the process is shown in the red line. In the red line, you press from from higher volume to a lower volume. That is the process called compression. And the patch stakes is part of the process, initial to final. We also have what we call basic equilibrium processes. That is, state remain particularly in equilibrium at all time. A state that remain in equilibrium at all time. This kind of a state is very easy to be able to analyze and to be able to understand. Work producing devices deliver the most work, and work consuming devices consume the least amount of energy. And that is the type of a process. So all these that you have been talking about, okay, this is another part of process. We have what we call state proselyte. Yes, state proselyte. That is another terminology you need to remember. What is a state proselyte? That is the thermodynamic state of a simple compressible substance is completely specified by two independent intensive properties. A process can go through a circle. When I say circuits, that is a process or a series of connected processes with identical end. Let's look at it. You have A go from two, that is from high pressure to a lower pressure, or from a lower volume to from a higher volume to a lower volume. It can continue as a process, and you see the path being like a circle. A circle continues to repeat itself, like the piston of a car, and so on and so forth. So all this that we have done today is to be able to remember the definition of terminologies. Okay, so we are going to still run through the terminologies because we must be able to define some of these terminologies in the exam. The first law, thermodynamics, contribute to the law of conservation of energy. I made mention of that we are still going to treat that when we get there. And this energy cannot be created, that cannot be this and that. Then what is energy? I will be talking of all energy. What is energy? Ability to do work. But in thermodynamics analysis, form of energy can be divided into two groups: macroscopic energy and microscopic energy. Two forms of energies, don't forget about that. Microscopic energy, that can be defined as form of energies are those related to the molecular structure of a system and the molecular activity. So the sum of all the microscopic forms of energy is called the internal energy of a system. And we normally use U to denote internal energy, capital U to denote internal energy. Then the macroscopic energy, the macroscopic energy of a system is related to the motion and the influence of some external effects, such as gravity, magnetism, surface tension, and so on and so forth. So the macroscopic energy can be considered into either kinetic energy or potential energy. Kinetic energy or potential energy. So again, what is kinetic energy? The energy of a system possessed as a result of its state of motion, and it's related to the speed, average speed, half mv squared. As you can see there, then what is potential energy? That is the microscopic energy we are talking about, the energy that a system possesses as a result of its position, yes, elevation under gravity. And the energy, which we denote by PE, is mgz, where m is the mass, g is the acceleration due to gravity, and z is the difference in elevation. That is that. Then the combination of energies, the total energy of a system consists of kinetic energy, potential, and internal energy. So the total energy equals to U plus KE plus that, and that will give you all that. That is the total energy. You should also remember that the unit of energy is in joule, kilojoule. You should be able to convert from that to that. You have what we call also the static energy. That is the total energy of a system that can contain or store in a system. The energy stored is called the static energy. Dynamic energy, form of energy not stored in the system and can be viewed as dynamic. Yes, the only mode of transfer of this energy is through interaction and within a closed system. Work and heat transfer. All these terminologies, you must remember them. I will not go back to define them again. I made mention of work. What is work? Work is the energy transfer, as you said, with force acting through a given distance. And you can define that expansion work, maximum work obtained when the external pressure is only infinitely less than the pressure of the gas in a system. And you can also define all those ones. So heat transfer, you can also define heat transfer as when no that is as energy that cross boundary of a closed system in two distinct forms, in form of heat or work done. So remember, three modes of energy transfer, we have done that before: convention, conduction, and reflection. As a student of this course, you must be able to go back, review all these three modes of heat transfer. Then we have exo, a process in a system that heat release to the surrounding. Exothermic, that is releasing of heat to the surrounding system. Endothermic, that is taking it in. Yes, a process in a system that is heated. Yes, it is produces its own heat to the surrounding. Then dynamic, word that permits eating for heat transfer. That is a boundary that allow heat transfer. Adiabatic, word that do not permit heat exchange of heat. Those are the things. So we have defined all these definitions, and we are moving gradually to where we're going. So total energy of a system is kinetic energy plus potential energy equals to the internal energy of the system, and they can be changed in internal energy, which can be delta U equals to delta Q. That delta Q is changed in heat energy, delta W. That is work done, expansion. Then delta E, that is additional work added to it in form of any order. So a system kept at constant volume, expansion work done is zero if the volume remain constant. So you're going to rewrite that equation in that form. And if it is a constant volume, what kind of system did you call that? What kind of a system do you call it if at a constant volume? Nobody. Okay. So when the system releases energy to the surrounding, the internal energy of the system decreases and it is negative. So work done by the system, heat loss by all these are stated there, you will see it. So I'm moving gradually now to where we are going. We have defined the terms that we'll be using as we go along, and there is no point that we say you don't understand what the term is talking about. So the internal energy, now we have a system, look at it. We have a system here with internal energy, work is done into the system, heat is given into the system. So the internal energy of a system is increased by transfer of either heat or work into the system. So you want to increase the internal energy of any system, supply heat energy to that system. Put heat energy to the system. So heat put into a system or heat absorbed by system is designated as negative heat because you expect your system to produce work. Okay? So delta U equals to Q minus W. Delta U equals to Q minus W. And you can also make Q the subject of the formula that Q equals to delta U plus W. So what he's talking about, the first law, that is internal energy equals to added heat minus work done by the system. Added heat minus work done by the system. Added heat minus work done by the system. This is a system you can think about. We have a mass and we have the pulley and then we have the stirrer. The stirrer has a pulley at the end and at the bottom inside the beaker that contains a liquid. The pulley is connected to the mass via a thread, and as you increase the mass, the stirrer will continue to mix the liquid so that the temperature will be distributed, and the thermometer will measure the temperature. You have the insulation, no heat is allowed to leave the system. No heat is allowed to leave the system. So a falling mass turns a product in an insulated beaker of water in the systematic or symptomatic representation of joules. And you see it, like mechanical work done into the system, the temperature increases produces by mechanical energy as a result of the mass going up and down. We also have another one here, that's another experiment that you can, that work could be done to lift a small weight, yes, a small weight out of the ground level. It can be done. So by the time the fan is rolling, you see that all the stuff, that is the pain, will be moving up here through the thread. All right. So there's another one here, which is heat is released by burning the gas. That is the piston of a gas. Then you have the spark plug. The volume keep on changing because it goes up and down. Yes, conversion of some energy to heat energy. Those are what we're talking about here. Then the internal energy of a system is increased by the transfer of either heat to this. That is the zeroth law of thermodynamics, that two objects in thermal equilibrium have the same temperature. Two objects in thermal equilibrium have the same temperature. Don't forget about that. We will still come back to all this. We are still just discussing all you have learned to review that with you and to take you into the course proper. So what is internal energy? We already defined it previously. We are not going to go back into it. Now we are starting proper at slide number whatsoever. So the first law says that the increase in internal energy of a system is equal to the amount of heat added to the system plus the amount of work done on the system. The increase in internal energy of a system is equal to the amount of heat added to the system plus work done on the system. That is what we have been describing before, and now we are turning it into the law. which we call the law of thermodynamics, the first law of thermodynamics. Don't forget, you must be able to state this law. You must be able to explain the law. So the increase in internal energy of a system equals to the amount of heat added to the system minus the amount of work done by the system. So delta Q equals to delta U equals to Q minus W. Remember, Q is the heat added to the system, and W is work done by the system. Every parameter here has a unit of work, joule. Don't forget that. So the first law of thermodynamics, delta U equals to, okay, we leave that. Work done by a movable piston now. We are going gradually. Look at the movable piston. The distance, the initial distance is from this point to that point, like you can see. And you have applied force pressing the molecules together. But the moment you press the molecules together, what does that mean? You are changing the volume. You move the volume from V1 to V2. That means there's work done because you are moving from this distance to that distance. So the work done is force times distance, force times distance, force times distance. And if you can play along this, force times distance, you can now say force times distance can now be force over area times distance times area. That means you have not done anything wrong here. You have divided by area of the piston and multiply by the area of the piston. There is no change. But you know that force per unit area is pressure. Force per unit area is pressure. And distance times area will give you volume, and that gives you the change in volume. So the work done here, W, will be P dV, P dV, P dV, according to the first law. So therefore, we can also talk that about the engine. Work done, work is always done. So what is an heat engine? An heat engine produces heat at high temperature to a given reservoir, and work is done out of that. Okay, so the thermal energy Q at Earth is introduced into the machine. You supply heat energy. Some of this heat energy that you supply is converted to mechanical work done to do some work for you, and some of the heat is released into the environment as a lower heat. In other words, QH equals to QC plus W. QH equals to QC plus W. And you can invert it that W equals to QH minus QC. That is allowed. We're still talking about energy. We're still talking about energy. So when we come to this direction now, what does the first law tell us about the heat engine? It's telling us that the change in internal system of the engine is equals to Q minus W. And W or Q is QC minus, QH minus QC minus W. That is what we have there. The internal energy of the heat engine does not change for circuit to circuit. So delta U equals to 0. Delta U equals to 0. So at the end of the day, your Q equals to W, and your W, which is work done, equals to QH minus QW. So the net heat flow into the engine equals to the work done by the engine. That seems to be a perfect, but there's no perfect engine. But that is what the first law is trying to tell us. Okay. All right. The first law again is telling us about the heat engine, and like we have written this down, this is equal to that, and that is equal to that. So again, okay, I think this is where we are going to stop today. Class, this is where we are going to stop today. And the assignment, due to what I have taught you, I have 26, 27, 29 people in class at last. 29 people in class at last. After 1 hour, I have 29 people in the class. So therefore, I know the number of people in the class, 29 people in the class, and the 29 people are Okupa. Just answer present. Moye Okupa. Are you in the class? That means it's not there. Oluwaseun Erinle, Oyebanji, Sogbamu, Tolani, Victor, Williams, okay, I'm coming, I think. Williams, that is where I stop. Okay. Abdulateef, Michael that was disturbing the class. Michael Adebukola, okay, that is your surname. Adebukola. Okay. Michael Adebukola, Adedeji Ayomide. Who is this? Akisi iPhone. You are not in class, oh. You are not in class. I say, and reporting our classroom. Don't use a funny name. Atafo, Austin Chukwudi, Awosanya, Padaru, Christian, Daniel, and this one to ask no name. Oh, well, they permanently remove him. Yes. Ebelechi, Ogbebu, Odulaja, Elizabeth, Ebosulu, and who else? If I have called you, you can go. I can see those that I have not called. Okoye Chioma, Mohammed, Fatima, David, Oyebanji, I think I've